I am going to discuss general structure and properties of negative feedback. These are the contents. Okay, I'm going to discuss. Now, first let us go for the definition of feedback. Feedback is defined as the process of returning part of output signal from a circuit back to the input of that circuit is called as feedback. Example. Okay, eh, the if any the human nervous system provides continuous feedback to the brain, especially when pain is felt for avoiding further damage to the body. Feedback systems are widely used in amplifier circuits, oscillators, and process control systems. There are two types of feedback systems depending on relative polarity of the signal being fed back into the input of the circuit. One is positive feedback, another one is negative feedback. Positive feedback is also called as regenerative. It is used in oscillators, comparators, symmetrical circuit to increase the gain. Negative feedback, another name is degenerative amplifier to reduce the gain, or we can say that stabilizes the gain. Now let us go to the general examples for positive feedback. In your bank account, okay, amount you deposited, okay, after 1 or 2 months, the bank will add up interest to your amount, so that total amount which is available in your account keep on grows. That type of feedback is called as positive feedback. In electronics, if we add two in phase same phase signals, so that we'll get larger output, this is called as positive feedback. In negative feedback, due to fever, the body temperature rises. You visit the hospital. Okay, doctor will give injection. The body sweats more, so that the body temperature drops. This is called as negative feedback. If you go to the electronics, if we add out of phase signals, then resultant output will be less or zero. That type of feedback is called as negative feedback. Now I'm going to move just how the negative feedbacks looks like. This is the general negative feedback. Okay, this is an open loop amplifier A. This is the feedback network B. Okay, input is applied. VI is applied to the mixer or adder or summation. Okay, then another signal which is coming from the feedback is VF. These two are subtracted, that is VI minus VF. This negative sign indicates that due to negative feedback, it indicates that feedback voltage always opposes the input voltage. That difference is applied to the amplifier so that output is reduces. Example, inverting amplifier or non-inverting amplifier. Like that, many examples are there. Let us move to the okay general negative feedback structure or signal flow graph of feedback structure. Here I am going to consider X is a signal that may be voltage or current, depends on feedback connection, where Xs is the source signal which is applied to the mixer or summation. See the symbol. Okay, here sign is positive. The actual input applied to the amplifier is Xi, and it amplifies this Xi and produces an output, that is X naught equal to A times of Xi, where A is open loop amplifier gain. Then X naught is sampled or fed back into the input of the feedback network. Output of the feedback network is XF, that is equal to beta times X naught. that is mixed with xs, so that we get xi equal to xi minus xf. This negative sign indicate due to negative feedback. We can say that the feedback signal always opposes the source signal, or we can say that the feedback signal having 180-degree phase shift with respect to source signal. This is the general structure. Let us go to the closed loop gain AF derivation. Okay. Now, from the amplifier, okay, x naught equal to a times of xi. It is amplified with a times. Next, xf is the output of the feedback network, or beta is the feedback factor. Output of the feedback network divided by input of the feedback network. It is xf by x naught. So that xf equal to beta times x naught. Xi equal to xs minus xf. This negative sign indicate due to negative feedback. Substitute xf equal to beta x naught in this expression. We'll get xi equal to xs minus beta times x naught. Then x naught equal to a times of xi. If substitute in this expression, xi equal to xs minus a beta times xi. Now you take this term into the left hand side of the expression. This minus will become plus xi plus a beta times xi equal to xs. Take the xi common in the left hand side. Xi into 1 plus a beta equal to xs. This is the equation number 2. This one is equation number 1. Divide, okay, 1 by 2, that is x naught by xs equal to x naught is a times of xi divided by xs is xi into 1 plus a beta. So xi in the numerator, xi in the denominator get cancelled. So that closed loop gain AF equal to A divided by 1 plus A beta, where A beta is the loop gain. 1 plus A beta is called as feedback factor. After connecting the negative feedback, the closed loop gain AF equal to A divided by 1 plus A beta means the gain is decreased by an amount 1 plus A beta times. Now let us go to the one more condition. If A beta is greater than 1, so that 1 is neglected. A in the numerator, A in the denominator get cancelled. So that closed loop gain AF equal to 1 over beta. Closed loop gain is the inverse of the feedback factor. Any doubt? Now I'll move to the properties of negative feedback. First property is gain desensitivity. It means that negative feedback makes the gain desensitizing the closed loop gain. After connecting the negative feedback, the gain will become desensitizing against the changes. Okay. Now I'll consider after connecting the negative feedback, AF equal to A divided by 1 plus A beta. This is equation number 1. Differentiate this expression with respect to A. DAF by DA equal to numerator into, sorry, denominator into differential of numerator is 1 minus numerator into differentiation of denominator. Differentiation of 1 is 0 plus differentiation of a beta will get beta divided by denominator square. So if you simplify the numerator, it will become 1 plus a beta minus a beta plus a beta minus a beta will get cancelled. DAF by a dA equal to 1 over 1 plus a beta whole square. You can rewrite this expression. DAF equal to dA divided by 1 plus a beta whole square. Now divide 2 by 1. 2 by 1, if you do it, DAF by AF, it is nothing but percentage of change in closed loop gain equal to dA divided by 1 plus A beta whole square divided by A divided by 1 plus A beta. 1 plus A beta and square will get cancelled. So that finally DAF by AF equal to 1 over 1 plus A beta into DA by A. DA by A is the change in the percentage of change in the open loop gain. So that the percentage change in AF is smaller than A because dA by A is divided with 1 plus A beta. So if you connect the negative feedback, the percentage change in the closed loop gain, okay, desensitizes as the gain. So that the 1 plus A beta is called as desensitivity factor. Now let us move to the second property, that is bandwidth extension. High frequency response of an amplifier with single pole. Okay, this is high frequency response where AM is the mid-band gain, beta is the feedback factor, feedback gain, WH is the upper 3 dB frequency cutoff frequency. Now, if feedback is applied to the single pole high frequency response, the mid-band gain decreases. If mid-band gain decreases, higher cutoff frequency increases to compensate. So how it will increases, we should show it in mathematically. This is for this graph, the mathematical expression transfer function A of S equal to mid-band gain divided by 1 plus S over upper cutoff frequency WH. Now, okay, closed loop gain AF equal to A divided by 1 plus A beta. Represent this expression in S domain or frequency domain. AF of S equal to A of S divided by 1 plus A of S into beta. Substitute A of S, okay, A of S, AM divided by 1 plus S over omega H in this expression, so that AF of S equal to A of S divided by 1 plus A of S into beta. A of S is AM divided by 1 plus S over omega H plus 1 plus AM into beta divided by 1 plus S over omega H. Now in the denominator 1 plus S plus omega H, if we take LCM, so that here 1 plus S over omega H plus AM beta, 1 plus S over omega H, 1 plus S over omega H get cancel, AM divided by 1 plus S over omega H plus AM beta, AM divided by 1 plus AM beta plus S over omega H. I'll take 1 plus AM beta as common in the denominator, so that AM divided by 1 plus S over omega H. This 1 plus AM beta will go to denominator here. So we can rewrite this expression AM divided by 1 plus AM beta. After connecting the feedback, the midband gain is decreased by 1 plus AM beta plus or in denominator 1 plus S over omega H into 1 plus AM beta. If you compare this expression with the transfer function after connecting the feedback, AF of S equal to AM of F divided by 1 plus S over omega HF. So that omega HF equal to omega H into 1 plus AM into beta. After connecting the feedback, higher cutoff frequency increased by an amount of feedback factor, that is 1 plus AM into beta. So that upper cutoff frequency increases. Similarly, let us move to the lower cutoff frequency. Lower cutoff frequencies decreases. How it decreases is, see, WLF equal to WL divided by 1 plus AM beta. If you derive it the same way as higher cutoff frequency, you get this expression. So that lower cutoff frequency decreases. Okay, let us see. After connecting the feedback, the midband gain decreases. Why it decreases? Because it is divided with the negative feedback factor 1 plus AM beta, so that it is decreasing. If it is midband gain is decreasing, obviously lower cutoff frequency decreases, so that FL becomes FLF, and meanwhile FH becomes FHF. Okay, so that overall bandwidth with feedback increases, and this is called as bandwidth extension. See, midband gain is decreases, higher cutoff frequency is increases, lower cutoff frequency is decreases, because it is division. Here it is multiplication, here also division. Final conclusion is gain bandwidth product is constant because mid-band gain is decreasing, bandwidth is increasing, one is decreasing, other one is increasing, so that it get cancelled, so that gain bandwidth product is always constant. Now let us move to the noise reduction. Okay, I will consider A1 amplifier having the gain A1, it having two sources. One is voltage source Vs, a signal source Vs, another one is noise source Vn. Okay, noise source Vn, it amplifies, produces an output V0. So Vs is the input signal, V0 is the output signal, Vn is a noise interface, An1 is the gain of an amplifier. This amplifier suffers from the noise, so that signal to noise ratio of this amplifier without feedback equal to signal power by noise power. Signal to noise ratio, signal power by noise power. This is the signal to noise ratio without feedback. Now, after applying the feedback, I'm going to cascade one more amplifier, that is clean amplifier A2. Okay, then Vs is a signal voltage, Vn is the noise voltage. Signal voltage is amplified by amplifier A2 as well as A1, but noise voltage only amplified by A1. Then negative feedback is provided. Now forward path gain, that is equal to loop, A1 into A2. Loop gain around the loop gain equal to A1 into A2 into beta. Feedback factor equal to 1 plus loop gain A1 plus A1 into A2 into beta. Output voltage, I'm going to write it, output voltage equal to signal voltage Vs is amplified by two forward gains A1 into A2 divided by feedback factor 1 plus A1 A2 beta, plus noise voltage is amplified by A1 divided by 1 plus A1 into A2 into beta. Now signal to noise ratio after connecting the feedback equal to signal voltage divided by noise voltage after amplification, Vs into A1 A2 divided by 1 plus A1 A2 beta divided by Vn into A1 divided by 1 plus A1 A2 beta. 1 plus A1 A2 beta, 1 plus A1 A2 beta get cancelled. A1 here, A1 here get cancelled. Vs by Vn into A2. Signal to noise ratio with feedback equal to signal to noise ratio without feedback into A2. Signal to noise ratio with feedback increasing means the noise is decreasing. It is called as noise reduction. Now reduction in nonlinear distortion. Just you see the curve A. Curve A is the output voltage versus input voltage. This is the curve A is without feedback, that is gain A. Curve B is after connecting the feedback, the curve B. So the curve A is here, curve B is here. It means that it is reducing. Why it is reducing? After connecting the negative feedback, the closed loop gain AF equal to A divided by 1 plus A beta, so that it is decreasing. It is here more non-linear distortion is there, means in the second curve, obviously it decreases because entire gain is decreasing, means whatever the nonlinear distortion also decreases. Now let us go for the example. If A changes from 1000 to 100 whenever it is without feedback. Now feedback factor equal to 0.01 at the time. What is the closed loop gain? AF1 equal to 1000 divided by 1 plus 1000 into 0.01 will get 90.9. For the second change, AF2 equal to 100 divided by 1 plus 100 into 0.01, it is 50. So see, the 1000 will be reduced to 90.9, 100 will be reduced to 50. Here the change in, let us move to the next, how it is what is the percentage change? You can, okay. Here you see the change in the gate without feedback is here 900. The percentage of change in the connecting the feedback is, okay, 40.8. Here more non-linear distortion is there. This it is reduced here. So this is called as non-linear distortion. Can you read out?